So here's a quick look at what we'll cover today. I'll start with a brief introduction to Nodka, who we are, and where we fit within the automation ecosystem. Then we'll talk about the shift that we're seeing in control systems, moving from traditional PLCs to IPCs and why that matters. From there, I'll share a real application story from one of our semiconductor customers and walk through how IPC hardware and CODESYS software work together in a unified solution. Finally, I'll highlight some optimizations we do at the BIOS and hardware level to ensure real-time performance before handing it over to Cesar for a walkthrough on setting up CODESYS runtime. So let me start with a quick introduction to Nodka. We design and manufacture IPCs, panel PCs, and HMIs specifically for industrial automation, focusing on high-performance, reliable hardware that is optimized for real-time control with software platforms like CODESYS. We have been in business for over 23 years, serving more than 5,000 customers across 30 countries, and have tens of thousands of automation PCs deployed worldwide. That experience has given us a deep understanding of what OEMs and engineers need, which is performance, reliability, and flexibility. We keep our platform open, so there's no proprietary software layer, so our partners can use a software environment that best fits their application. We serve a similar space as other leading IPC manufacturers, but our main focus is on the control and visualization hardware for automation user. Our goal is simple, is to provide the solid hardware foundation so our partners can focus engineering on the application itself. So here we have a diagram that shows the full automation product landscape. Our role is highlighted in green. We support the ecosystem at 2 points, the controller layer with the IPC and the operator interface layer with the HMIs. So from PLCs to IPCs, a shift in control systems. PLCs have been the backbone of automation for decades, and they'll continue to play an important role. But as application demands more data, connectivity, and precision motion, IPCs are increasingly being used or used alongside with PLCs to take on the heavier computing tasks. With softwares like CODESYS, IPCs combine the computing and control on one open platform, supporting multiple protocols, seamless IT and OT integration, and direct cloud connectivity. They also offer flexibility, allowing you to mix high-level languages like C or C++ with traditional PLC programming for more advanced motion and robotics. So instead of replacing PLCs, IPCs expands what's possible, giving automation builders more power, openness, and scalability on a single platform. So here is a real-world example that shows this in action. One of our customers in the semiconductor manufacturing needed a motion controller for a wafer handling robot, something that demanded extreme precision, high speed, and consistent throughput. Their solution was built on one of our industrial IPCs with the BIOS tuned for real-time performance and running CODESYS runtime as a control platform. Through EtherCAT, the system managed multiple servo drives and motors in perfect synchronization. The result was a high-speed, high-precision robot that can move wafers reliably and safely, all built on an open standard-based architecture. And this same architecture applies across other industries, from multiple axis CNC system to robotic arms, wherever high-speed synchronized motion is required. So traditional motion controllers already do a great job with precision and reliability, but as systems become more complex, they need openness, faster data handling, and better integration with modern software environments. That's where IPCs running with CODESYS really stands out. They bring together real-time motion control and PC-level computing in one scalable platform. This is what enables OEMs and integrators to design their own automation controllers, combining CODESYS logic, EtherCAT communication, and high-performance IPC hardware in a single system. You can see that reflected here in this architecture, a unified 3-layer setup. The IPC runs CODESYS runtime as a motion controller, the HMI provides visualization and operator control, and the EtherCAT connects drives, IOs, and sensors for synchronized communication. The result is a clean, connected system, control, visualization, and communication all working together seamlessly, designed for we talk about real-time performance, it's not just about the software, it starts at a hardware level. A standard IPC is great for general computing, but out of the box, it's not designed for deterministic control. Features like power management or dynamic clock scaling can introduce timing delays, and that's something we cannot afford in motion control. So with the motion control IPC, we tune the BIOS specifically for CODESYS, enabling the EtherCAT master and activating Intel TCC mode. This ensures the consistent cycle times, stable synchronization, and reliable motion performance, even under demanding workloads. So TCC mode is a key part of what makes our IPC motion ready. It starts by locking down the CPU, turning off power management and turbo boost so your control loops run at a fixed rate. Next, it isolates system resources by disabling hyperthreading and dedicating cache specifically for CODESYS, preventing background processes from interrupting motion control. Finally, it aligns with CPU timing with the EtherCAT communication to maintain a precise synchronization across all devices. In motion control, even microseconds of jitters can cause drift or vibration. TCC mode eliminates that by ensuring every control cycle execute exactly when it should. So this is where everything comes together. On one side, we have the hardware, our motion control IPC, tuned at a BIOS level for real-time performance. On the other, we have CODESYS platform, flexible, open, and standard base. And when you combine the two, you get a complete motion control solution. The IPC handles the control logic, the HMI provides the visualization, and the EtherCAT connects everything in real time, from the controller all the way down to the drives and sensor. The result is a system that's easy to deploy, reliable, and optimized for for high performance motion. So whether it's in CNC milling, robotics arm, high-speed pick and place, this integration of CODESYS and our real-time IPC gives OEMs a proven, flexible foundation, the performance of a dedicated motion controller, but the openness of a PC platform. So what does that mean in practice? For motion controller builders and integrators, it means starting with a hardware platform that's already optimized for real-time performance and pairing it with a flexible software environment like CODESYS. That combination takes away the complexity of building from scratch. It speeds up development, improves reliability, and gives teams the freedom to scale into robotics, CNC, semiconductor applications without being locked to a closed ecosystem. For OEMs and machine builders, it shortens development time, improves motion accuracy, while allowing future scalability through software updates with hardware performance and I/O defined to match each application's requirement. And most importantly, it lets engineering teams focus on what really matters, which is their application, instead of worrying about the foundation underneath. Okay, so far we have looked at Nodka's IPC and CODESYS working together to build a motion control platform. Now that we have seen this architecture and the results, I'll go ahead and hand it over to Cesar, who will walk you through the next part, which is installing the CODESYS runtime on one of our IPCs and configuring the EtherCAT master and slave devices.
Thank you, Eddie. Let me share my screen. Okay. Okay, can you guys see my screen? Yeah, that's good. I think. Okay,
Yes.
so
Thank you.
thank you, Chris. Hello everyone. My name is Cesar Hernandez, and I'm with the technical support team at Nodka. Thanks for joining us here today at the CODESYS Tech Talk. So then the first part of this presentation, Eddie covered the application of a motion controller using an RIPC and CODESYS. And on the second part, we're going to cover some initial steps for deploying a CODESYS demo on a Nodka IPC using the I/O modules as the slave devices and controlling them using the CODESYS framework. Okay, so we've broken down the process into 6 main steps. First, installing the real-time Ethernet driver on the IPC. And what this does is establish a communication link with CODESYS and the hardware. Second, we will create the project under the CODESYS IDE. Next, we will import the hardware description files. These are XML files so that CODESYS can recognize the I/O modules that we are using. Then after that is the device discovery, where we will use CODESYS to scan the network to find the connected hardware. After that, we will program the control for the IOs on the CODESYS IDE. And then finally, we will see the sample application output on the IPC as well as the visualization on the CODESYS. So before we begin, let's quickly review the setup for this demonstration. On the left-hand side, we have the CODESYS IDE installed on our development computer. Connected over Ethernet. In the middle, we have the optimized IPC with the CODESYS runtime installed. And then this will become our EtherCAT master, which will be connected to the EtherCAT IOs, which will become our slave devices. And today we'll be focusing on our action modules to turn. So these modules are to turn devices on and off. While we are only using digital outputs, this is a fully modular system. So remember that you can easily add other I/O slices for different needs. Some for reading analog sensors, other for temperatures or high-speed encoders. Okay, so the first step is installing the Ethernet driver. You can't just use a standard Windows network driver to make the IPC as an EtherCAT master. This slide demonstrates how to update an existing standard Ethernet driver to bypass the Windows network stack for real-time access. And with the CODESYS specific Ethernet driver installed on one of the dedicated ports on the IPC, this gains direct access to the hardware via EtherCAT. So we'll see right here in the first video how to install the real-time Ethernet driver. So first we start by going to the device manager. Then we're gonna go to the network adapters. And for this instance, we're gonna use number 4, which is in this case, the one that's gonna become the CODESYS real-time Ethernet driver. And by installing this specific driver, the generic port is now capable of handling industrial Ethernet protocols, such as EtherCAT. So we're gonna pick from our disk. We see that we have on our main IPC. We go to the desktop. We open up the Ethernet driver. We click OK, and we go to next, and that's it. We have dedicated this port to the CODESYS Ethernet driver. Now we can use this as to be able to connect to CODESYS. So now with the driver installed, the next step would be installing the CODESYS control runtime. I believe most of you already are familiar with installing the CODESYS runtime, and if you're not, you can get in contact with me or Eddie later after the presentation to have a copy of this presentation or for a more detailed guide about this demo. For time's sake, we're going to continue to the next slide. Okay, so alrighty, with the runtime and Ethernet driver installed on the IPC, we are ready to configure and program the IPC controller using the CODESYS IDE. So the first thing we need to do is create a new project in the CODESYS IDE. Then we connect the CODESYS IDE directly to the IPC over the network. We then select the IPC as our target device. And finally, the last step is to build, deploy, and run the application on the IPC. Okay, so we're going to start by creating the project. We open up our CODESYS IDE. We're using version 3.17. So we go to the start new project. We're going to select a standard project for this demo. Okay, now we're going to rename our project to IPAC demo. And we're going to choose a location where we want our project to save. In this case, we're going to choose the default location. We press OK. And then for this next step is crucial because we're going to select the CODESYS control runtime for the device from the drop-down list and to ensure that it's compatible with the runtime that we installed on the IPC. Next, we choose a programming language for our main program block. For the programming language, we're going to use the default option, structured text. There's different languages, but for this demo, we're going to use structured text. And then you can see that our project trees created, and we don't have any connection yet for our device. And this is where we're going to input our functions. Okay, now that the project has been created, we're gonna connect the CODESYS runtime installed on our IPC. We're gonna make that connection to the IPC. So to start, we double click on the device, and then if you see, we have no connection yet to the IPC. But since we already installed and ran the runtime on the IPC, you can see that it's already detected by CODESYS. So this is our IPC right here, the desktop wrap dome, and then so we double click on it, and you can see the connection is already established. We click OK. We're gonna select our login information, and you see that our device. Our IPC is now connected to the CODESYS IDE. Okay, so with the demo project created and the IPC connected to the CODESYS IDE, the next step is to let CODESYS know about our specific hardware. In this case, our I/O modules. And we do this by importing the hardware descriptions. We import the device description files to the CODESYS IDE, and these files are XML files that are provided by Nodka. And think of these files as like the digital blueprint for the IOs and the EtherCAT modules. They give the CODESYS IDE the information it needs to be able to recognize and communicate with the devices. Okay, so to import the hardware description files, we go to the Tools tab on the CODESYS IDE. We open up the device repository. You can see there's already different devices installed on the CODESYS IDE, but for this instance, we're going to use our Nodka IO module. So we go to install, and you can see our XML files for the device descriptions are already here on our main computer. We click on the XML file, and you can see that CODESYS now recognizes our IO modules. In this instance, we're using the AL2019 and the AL2319. Okay, so we go to the next slide. Now that our project knows what our hardware is, we can perform the device discovery to find the devices on the network. So first, we add the EtherCAT master to the project. Then instead of adding each IO module manually, we simply just use the scan devices button to detect the devices on the network. So CODESYS will detect the devices automatically already. And then because we already imported the hardware descriptions, CODESYS doesn't just find them, right? It knows exactly what they are and knows the configuration of those IO modules and making it easier for us to program. So we'll assign the correct network adapter for our EtherCAT master and log into the controller and scan all the connected IO modules. So you see right here, we added an EtherCAT master. We go to the MAC address, we log into the device. Press OK, and then you can see the CODESYS Ethernet driver that we installed on our IPC is already there. So we press on it. And now we can log into the device by pressing the login button on the CODESYS IDE. Press yes to connect to our device, and then After this, we could go to the EtherCAT master on the project tree, right click, and then scan for any devices that are connected. And CODESYS will automatically detect all our I/O modules that are already connected to our IPC. We'll copy those to our project, and now we're ready for them to be able to program the I/O modules. Okay, so now with our I/O modules discovered and configured in the project, we can now move to the programming the sample application. And we're going to be using the standard IEC 61131-3 language structured text, the one that we chose on the beginning of our project creation. And we're going to implement this code on our demo. And so what this code is going to do is going to just read the LEDs of our I/O modules connected. As you can see in this diagram, we see we're going to use the structured text to be able to connect to these I/O modules on the IPC. Okay, so we will also need to create the connection between the software and the physical hardware by mapping the physical I/Os to our program variables. So this is broken down into 3 steps. These channels are available on our I/O modules. So first we need to identify the I/O channels, and then we assign the program variables to them. And this creates the link between the hardware and the program logic. And finally, when we're done completed the mapping, we'll be able to run those LEDs on the I/O modules. So this is how we control how we program the control logic and map it directly to our physical hardware on the IPC. So first, we go to the program function to create the program function block. You can see we already added the variable declarations onto our program. And we added an array for the LEDs. So we're gonna index them from 0 to 15, and then the logic will be a chaser pattern, a light chaser pattern that will appear on the I/O modules. So we go to the I/O module, and then we go to the the mapping section. You can see we already mapped out our I/O modules right here with an array index 0 to 15. So if you want to map them out, we just click on the ellipses, and then you can see that we have the array right here. And so we click OK after we map them out, and then we just do the rest of them. Okay, and then we also have a coupler installed as well, and an external I/O module connected to it. So we just do the same thing on that one. We go to the mapping, and we map the I/Os. And this time we map them out backwards, so 15 to 0. Okay, so and so here's the final application output. We have 2 videos side by side showing the CODESYS sample project running on the Nodka IPC. On the left-hand side, you can see the physical device output with the light chaser pattern running on directly on the I/O modules. And on the right is the CODESYS application output, and this is a visual also running on the HDMI display connected directly to the IPC, and also shown on the CODESYS IDE. So the visualization is also shown on the IDE. And so to quickly recap this part of this presentation, this demonstration covered 4 key steps. We established the foundation. First, we established the foundation by installing the real-time Ethernet driver to create the IPC as an EtherCAT master. Next, we defined the system with the XML hardware description files to discover and add our I/O modules to CODESYS. Then we bridged the software with the hardware. We mapped out the physical I/Os and added the control logic to the project. And finally, we we're able to build, deploy, and run the CODESYS sample application on the IPC, controlling the I/O modules. And that about covers the main flow for this walkthrough. Once again, thank you for joining me and Eddie and Chris and all the CODESYS team here today. And I'll hand it back over to Eddie for any final thoughts.
Okay, thank you, Cesar. So yeah, I'll go ahead and just take this screen back real quick just for the, quick closing. Yeah. So yeah, I want to go ahead and just thank everyone so much for your time and attention. Thank you, CODESYS team, as well as Chris, as well as the rest of the presenter. Very knowledgeable. I'm very excited to be here. So that brings us to the end of our session. We covered how Nodka's optimized IPC hardware combined with CODESYS creates a reliable, high-performance foundation for motion control in robotics, CNC, and semiconductor applications. Of course, if you'd like to learn more, you can find our data sheets, guides, and solution details using these links posted here, or feel free to reach out to our North American team, which is myself and Cesar. We'll be happy to connect and discuss, any questions or projects you may have. At the end of the day, Nodka, our focus is to enable OEMs to build high performance motion controllers faster, simpler, and scalable, helping engineers and OEMs push what's possible in automation. And once again, I just want to thank everyone for joining us today.